Item today. We have Magnus, who's going to talk about testing threaded C and C++ code with his Nidhugg tool. Let's give a round of applause for Magnus.
Yes, hello. My name is Magnus, as I was introduced. I'm a PhD student at Uppsala University in Sweden, where I research tools and techniques for testing concurrent software, for example, when using threads. And I'm going to talk to you a bit today about one of the tools we have worked on for a while, and in particular help you to understand how it works well enough so that you can apply it yourself, because it isn't really that hard. So the target audience for this talk is the non-computer scientists. So if you do computer science, you might get slightly cringy because I use imprecise language in some places, and you'll just have to live with it. The point of this talk is to make basically anyone who needs to be able to use these kinds of tools. And really, the things I'm going to teach you today are things that are not specific to this tool, really, but things that you need to know to use any tool in this entire category. So even if this particular tool isn't what you need, maybe you run a different programming language, you do a different programming model, there are probably similar tools for those, or there might be in the future, and in that case, the skills you learn here will be perfectly transferable to that. So the talk will be mostly centered around me showing you a bunch of examples. So I will show you a bunch of code with various bugs that I either introduce or, or fix, and show you how to apply these tools and what they can do. I will also talk a bit about weak memory models, since that is something that comes up a lot when you do threaded programming, and is one of the harder parts, and how these types of tools help with that. And finally, I will show an example of us testing some very non-trivial real-world code from the Linux kernel, so that you can see that this is not just a tool for toy examples, even though most of the examples I will show are toys, because that's the way we can fit them on a 45-minute presentation. So, this is a very boring introduction, but parallel programming is hard, right? You've probably seen this picture before. It's from Mozilla headquarters, and the text on the wall is probably not readable, but it says, "Must be this tall to write multi-threaded code," and here's a standing desk. So the point is, everyone makes mistakes when writing multi-threaded code, because it's just so much to think about, and the space of things can happen just explodes. And another thing that makes it very hard is that at testing, which we usually use to verify that our software does approximately what we want it to do at least, doesn't apply as well to multi-threaded software, because if you run it twice, a multi-threaded program, it might do something different a second time. So your unit tests might run fine one day and then fail the next day. And this is undesirable, and in fact, having passing tests doesn't mean so much in that context. You might be aware of tools, of race detection tools like Valgrind and Thread Sanitizer, right? Those of you who have done threaded programming probably have at least heard of these. So these tools instrument your program beforehand, and they will create warnings during runtime if your program does things that apply to some heuristics they have for bad behavior, for some definition of bad. But unfortunately, these things too do not give guarantees. Even for the types of problems they do look for, they do not guarantee to find them. But all hope is not lost, because there are tools that can give these types of guarantees. And this is what I'm going to teach you today. So Nidhugg is a tool. It's a program you compile on your computer, and you run your unit tests through them. So you write your unit tests as normal. They have to be unit tests, though. That is, they have to be programs that don't take any additional input. You cannot test interactive programs this way, for example. And what Nidhugg does is that it just runs your tests several times and actually systematically tries all the possible things it can do due to the way multiple threads interact. And thus, because it tries everything, at the end you have a guarantee that if it can crash, Nidhugg will find it. But also, unlike things like, unlike race detectors, there are benign data races, but Nidhugg is designed, these types of tool doesn't need to be that way, but Nidhugg is designed to not complain when you have benign data races. So what it looks for is what you would look for when you run your unit test. You look if it crashes or the output is wrong or something like that. So Nidhugg is designed to work on the level of LLVM bitcode. So what you do is you take your unit test and you compile it with Clang to a LLVM bitcode file. You can link these together. This command is not very commonly used, but it exists. You can link them together if you have multiple source files. And then you give that to Nidhugg and it runs it for you. There are also other ways. For example, if you have a bit of a bigger program, if you have an entire build system, there's a wrapper script around Clang called WLLVM, which is a bit of a mouthful, but it is a drop-in replacement for CC, and it will generate bitcode even using a build system that doesn't know this thing. And there's also a convenience front end if you just have a single C file, which is what we're going to use for most of the day. Yes, so Nidhugg is open source and available on GitHub. So if you really want to look at the source code, feel free. That's not really what you need to be able to use it, but it's freely available. So let me show you a very basic example of a concurrent program. So this is a program in C, as you might be able to tell. Is it large enough for you in the back to read? Yeah. Which we have a main function, which spawns an additional thread T, and then writes a variable, and which is a parameter to this thread T. And thread T does something and assumes that its parameter is already set. So is the program correct? It's not. Right. So let's try to run it and see what happens. So Clang example 1. We need to say p thread, I believe. Then a.out. And it doesn't crash. The assertion doesn't fail. Maybe we were just unlucky. Seems fine. Oh, well, I've toyed with you enough. Of course, what can happen is this can happen before that. So let's see if we try to run this thing with Nidhugg, if what it says. So we say Nidhugg, and we say Nidhugg C, which is the front end that takes C code as an input. And we tell it which memory model we want. If you don't know what a memory model is, just ignore this for now. I will get to that in the future. And we give it input file, and it produces a bunch of output, but the interesting part starts here. So this means that Nidhugg ran this program twice, and after that it found a problem, which is assertion variation, which is this x equals to 1 we had. And above the error message, we have a trace of what the program actually did to come to that point. So this thing, this bracket 0 other bracket, means the main thread. And then 0.0 is the first thread spawned by the main thread, and so on. So these are the thread identifiers that Nidhugg creates for itself. And the execution of this program went like this. First, we spawn the thread. In this case, the Clang debug info isn't quite precise enough to give us the correct message here, but this is the thread spawn, since afterwards we can see the second thread running. And then the second thread runs, performs the load of x, upon which we run the main thread again and write 1 to x. So obviously we have loaded whatever was in x before it was written, which is probably 0, since this is a static variable. And then finally the program crashes because of this. Okay, so this is what Nidhugg does, right? It runs the program a couple of times, 2 in this case, because there are 2 behaviors of this program, and it sees if it can make it fail. How does it do this? So Nidhugg takes your program and runs it instruction by instruction. It doesn't actually create multiple threads, but rather whenever there are multiple threads that can run, it arbitrarily picks one of them to run in a single step. So this trace we saw it corresponds very closely to what Nidhugg actually did internally. So it executes a first execution of the program, which it just picks arbitrary threads to run. So in this case, it picked the non-crashing case as the first execution, and then it finishes that, and then it does some analysis. So who here can tell me the traditional definition of a data race in shared memory programs? You have probably seen this before, but I'm sure you're a bit shy in case I'm going to say something very academic. But the definition typically reads something like this: 2 threads accessing the same variable, and at least one of them is writing it. And if you have this, then the order of these 2 accesses matter, right? Because the write changes what the read will see, or if you have 2 writes, you change what the end result will be. So Nidhugg looks at these races. It also considers other types of races than data races, like the order of which 2 threads, which gets first to get a mutex and so on. But it looks at these types of races, and it tries to see if it can change the schedule it just executed so that they are run in the different order. And then it puts all these executions in a queue, and then it just restarts running your program, replaying up until the point where the race comes, and then playing that in reverse, and then arbitrary execution afterward. And then you just repeat this process until you're out of new behaviors to explore. So this is the conceptual model. Let me show you a figure of what it did on this very trivial example we had that I showed you. So we start by running the first thread twice, creating another thread, and then writing to x, and then running the second thread. And then it is done. So Nidhugg then sees this race between the read of x and the write to x, and puts in the queue that it wants to execute after spawning thread t. We want to immediately switch and execute t. So it puts this in the queue, and then, since there are no more races in this program, it restarts execution, picking one of these executions from the queue, and it runs it to completion, and then it finds the assertion failure. So conceptually, this is what Nidhugg does. Doesn't seem so hard, right? So that's all fine and dandy, but what are the limitations, right? Surely this is just something that works fine for examples, for tiny toy programs, but breaks down when you run it on larger code. So what are the limitations of these techniques? Well, it's actually quite simple. There are basically 2 hard limits on these techniques. The first limit is that the input program, the unit test, must be deterministic. So what that means is that every time Nidhugg reruns your program, it must do the exact same thing it did the first time. So you're not allowed to look at what the time is and branch on that, like a random number generator would do. If you do file I/O, you have to be very careful. Some tools could conceptually intercept these things and make sure that no funny business is going on, but Nidhugg does not do this. So if you do file I/O, you should probably make sure you are only reading and that you are closing all your file descriptors before you start your threaded workload. There are also a second limitation is in that the program must not run forever. And this is a bit tricky to explain, so I will instead show you what it means, because I think that will make it a lot easier to grasp. But the problem with running forever is that this implies that the program has either infinitely many behaviors or that it doesn't terminate, in which case Nidhugg just gets stuck, right? Because it actually runs your program. Let me show you a second example. So say that we wanted to fix this program, but instead of doing the obvious thing, we introduced a queue data structure. So this is, hold on, this is not supposed to be there yet. So this is the same program, but instead of having a global variable x, we use a library that provides a FIFO queue. And this queue, we can put integers in and take integers out. And we use this queue to shuffle integers between the main thread and T, because we hope this will solve our race condition. Right? Now our program will work. So the queue interface is a bit peculiar in that the enqueue operation always succeeds, but the dequeue operation might return either true or false, depending on if the queue is empty or not. So in order to make sure that we actually get the number we want out of it, we just have to loop until it succeeds. So let's see what happens if we try to run Nidhugg on this program. Terminal, example 2. Oh, copy header files as well. Okay, and this is, yes, so we're getting into the nitty-gritty already. So I told you that Nidhugg would only complain about real errors, but there is some exceptions to that just through, this is just some mess in the interface really. But here we have a sort of a warning of strange behavior that is opt-out rather than opt-in. And what it says is that this queue data structure uses mutexes, but it doesn't call init on them because I was too lazy to. I didn't want to put an init function here. So instead I use static initialization, and so you have to add a really long command line, which is in the help text, so you don't have to memorize this. And then it works. Well, I say that, but there doesn't seem to be much happening, right? It's just standing there and doing nothing. Let's add another flag, print progress. And it will print how many behaviors it has explored already. 400 behaviors, 500 and counting. So something is strange, right? This program isn't very complicated, but it just keeps going. So the problem here, what Nidhugg does is that it will first run an execution where the queue operation succeeds on the first try. And then it will see that it can change the behavior of this thing by switching it with this thing. So it switches them, and now try the queue fails the first time and then succeeds. And then in the second execution it sees, oh, we can switch it with enqueue again to make it fail twice. So it switches it with enqueue again, and okay, now we have an execution where it fails twice. Well, now we have yet another call to the queue, which we can switch with unqueue, and then we can make it fail 4 times. And it will just keep going like this forever. So this checking will never terminate, even though it is quite obvious to you and me that this program must terminate at some point, because eventually the main thread will call enqueue. So there are a couple of things we can do about this. because and those things are based on the observation that this is basically the behavior of the program doesn't really change based on how many times this loop runs. That even if this loop succeeds on the first call, it will do exactly the same thing as if it succeeds on the 10th execution. So what we would like Nidhugg to do is just to try to run the program once, really, because that is all that is actually required to see all the assertions and have them read all the things they can. So there are a couple of ways to do this. One of them, since we have one of these loops that if it fails and loops, it has no side effects. We can replace it with a special intrinsic that is actually not unique to Nidhugg, but has a bit of a complicated name anyway, called verifier assume. So if we have this intrinsic, if we call this intrinsic with a 0, let me just show you what happens. This will make the tool abort execution of the part of the search tree, the tree I showed you before, where the verifier assume 0 call is placed. So if you just place it in main, we are just aborting execution before anything interesting happens, and we are seeing nothing, right? So even if we change this assertion to, say, local is 2, it won't even find it, right? We are terminating immediately. But we can use this to turn a pure loop like this. If we pass the success value from the queue to assume, now we're suddenly ignoring the case where assume fails, where the queue fails, because as we argued before, this doesn't change this doesn't add actual behaviors, just behaviors as far as Nidhugg is concerned. So now I didn't change the assertion back, so obviously the local is not 2. But if we change the assertion back, we can see that Nidhugg, after exploring 2 traces in this case, because it needs to actually run the second trace before realizing it calls assume 0 and is uninteresting. We are able to check this program as well. So fortunately, in real-world code, these things are not so common. They're usually in like low-level threading primitives, and above that you have blocking behavior or other stuff that makes it so you don't have to do these kinds of things. So Nidhugg can actually do this on its own for code that isn't so complicated. So I had to introduce this queue data structure to even be able to fool Nidhugg to do this evil thing, to not terminate here. But there is another thing you can do if you don't want to change your code, right? Because that is sort of icky if you have to introduce if-defs and stuff into your code just to be able to test it. Nidhugg also has this flag called onRoll, which is a bit more heavy-handed and will basically force any loop you have in your program. So this is the only loop here, to never be executed more than some number of times. So in other words, it just uses this assume mechanism to stop it. So if we say onRoll equals 10, it will execute a program 10 times, and then the 11th, it realizes it has gone too far. So this is a way to do it without actually touching your code. But obviously, you will have to consider all your loops in your program, that you are not actually preventing it from doing some interesting behavior, because using these tools, you can very easily prevent yourself from finding real bugs if you are not careful. So that is the icky part. You either use verifier assume, and basically you cut off a part of this tree that Nidhugg builds of different orders it can explore, or you use onRoll flag, and prevent loops from going further than a certain point. So that's it about limitations of these techniques. So let me show you some other things that you might encounter. So say that you have a program that is calling a library, and this library is not part of the files you are feeding to Nidhugg. In this case, Nidhugg will let you do this, call functions, such so-called external functions, but it will very pessimistically assume that these functions will go and touch all the memory you have, just to be safe, that it doesn't miss some kind of strange behavior. So it will definitely basically reorder this function with every other memory access you have that it can. And obviously, if you are using external functions, sometimes this is undesired behavior because it makes Nidhugg run really slow, because there are just so many permutations of these things to try. So you can avoid it to do this by promising to Nidhugg, and of course, if you break your promise, then Nidhugg will not give you any guarantees anymore. But you can promise to Nidhugg that this function has no side effects. It will not change its behavior if it's reordered with something, and it will not touch any memory. So an example of this is if we take the program we had before, right, and we want to see what it actually does. So we add some printf statements here. Now if we run this example, so we use the unroll flag here as well, you can see that it runs it a lot more times than the 11 we saw before. And what is actually happening here is that it is interleaving this waiting call into enqueue in every possible location it can find where it might do something interesting. And this just explodes the state space. But obviously, the only side effect printf has is that it puts stuff on screen in this case, which is a side effect we don't want Nidhugg to look at. So if we use this extra flag, we get the 11 traces. And if I decrease the unroll count, we can use this to see a bit the different traces it was exploring, right? First it immediately enqueues, right? If we look at the source, I have a starting message first in print. I don't need to pack it this hard. And then it creates a thread, and then it prints just before putting something on the queue. And then we get a waiting message for every time the queue function fails. So the first execution, the queue immediately succeeds. Second one fails once. This message is actually the other way around, because obviously it's not atomically executed together with the enqueue function. So, and in the last execution executes it, it fails it twice, just like we saw before. Or well, I told you before that it would, but now you can actually see that it does this. All right. So let's talk about this thing called weak memory. So just so I have some perspective, can we do a show of hands? How many of you know of weak memory models already? Okay, not so many. All right, good. So just to add insult to injury, to make threaded programming even harder, CPUs don't actually execute code like Nidhugg does, just picking a thread and doing it, and then picking some other thread and doing it. It actually executes it in a way that makes it behave as if the statements in your program are somehow changing order from the way they appear in the source code. But this behavior only appears when you write multi-threaded code. So this is obviously very painful if you are writing multi-threaded code. And on an Intel machine, for an example, when you do a write to memory, it will not actually take this write you are doing and put it immediately into memory, but it will just put it in a buffer in a queue somewhere in the CPU, and then it will keep on executing your program. And then at some later point, it will take this data and then put it into the memory system. And this makes your program. Do you have a question? Well, yes, indeed. So, as I will tell you, Nidhugg will allow you to see that the way the CPU does these things, or can do these things, according to its specification at least, and you can check if you insert barriers, you can check that you have done this correctly. So, yeah, this buffer effect I talked about, which appears on the Intel, but also on most CPUs actually, and most CPUs actually have more behaviors, but Intel is relatively nice to you in this regard. So the memory model in which this is the only kind of strange behavior you can see, is called the total store order model, and Nidhugg can test programs under this model with the same kind of guarantees that you get without that. So if the CPU is allowed to do these kinds of strange things, Nidhugg will find it and tell you that your program will fail under these conditions. However, there is a gotcha, and that is that it does this by simulating these behaviors, right? It doesn't actually create more threads. And if you call an external function, it doesn't know what that function actually wrote, so it will not simulate these things. So if you are using external functions, please don't. Please just compile them into your input to Nidhugg, because that way you can keep your guarantees. So let me show you this, because I'm sure it's a bit hard to understand just by me speaking. So here I have a relatively simple program. Again, I'm using variables directly. In this case, I use volatile to trick the compiler to do the right thing, but you should probably use C11 atomics. I just didn't because it makes the example shorter. But some tools like Nidhugg will scream at you if you don't use C11 atomics, because this is, well, with volatile it isn't, but what I showed you before is actually undefined behavior. But if you were using C11 atomics, you would get the same behavior that I've already shown you. So let's take a look at what this program does. So it has two threads in this case. The main thread only spawns these threads and then stops. So the interesting behavior is in these two threads. And these two threads have two variables they communicate via. So T1 first writes to one of the variables and then reads the other. And whereas T2 does the mirror thing. So it writes to the other variable and then reads the first. And this is part of an good old mutual exclusion protocol. This is supposed to guarantee that these printfs, which are sort of the critical section here, will not both be executed. So is this true? Is it possible for this program to print fizzbuzz, or buzzfizz for that matter? One person is nodding. Someone else is shaking their head. Okay, so yeah, it's sort of a trick question, because obviously if we just look at this model where one thread is executed at a time, either T1 is writing first, and in that case, it's impossible for T2 to read 0 here, or T2 is writing first, in which case it's impossible for T1 to read 0. And if we run it on the Nidhugg, it will also tell us as much. So it executes the program 3 times. First time it prints fizz, second time it prints nothing, because this was just a section of the code, and the last time it prints buzz, but it never prints fizzbuzz, right? But remember this thing I put here on the command line that has now grown quite long. I can delete some things to make it easier to read. this SC thing. So SC stands for sequential consistency, and it's just the technical name for this model where one thread executes at a time. But let's see what happens if we replace this with TSO, which is what I talked about before. Suddenly, Nidhugg executes your program 4 times. And the last time it actually prints this thing that we were hoping it wouldn't, this spooky fizzbuzz, this thing that shouldn't be possible. And either X is written first or Y is written first, and yet both threads will read 0 here. And this is an actual behavior. Like if you write this program and run it a trillion times on your Intel CPU, eventually it might do this. And for a bit larger programs, this will appear frequently, but since it's so small, it's sort of hard to get a real CPU to do this. How do you fix this? I mean, if you have this, now we're not talking about how do you fix this with Nidhugg, how do you fix your program? I mean, your program does something you don't want it to do, right? So a guy in the audience talked about fences. So there is this thing on x86, for example, you have this special instruction called mfence, I believe. And then I just add some stuff so that the compiler knows what this thing is. So if we shove this magical instruction in, this barrier instruction in, now suddenly an x86 CPU, some Intel CPU, is not allowed to let this instruction go below this instruction. So the barrier sort of prevents this kind of weak memory behavior. So let's see what happens if we run Nidhugg on this thing again. So now we're back down to 3 behaviors. And of course, you should probably not use assembly intrinsics unless you're doing low-level like embedded programming, or unless you really have to. And of course, you can write the C11 equivalents here, which is a bit longer. So I will show you an similar thing. So if you use C11 atomics instead, these by default, unless you use the really long form of load and store, do these kinds of fences for you so that it will not behave this way. So also if you do it this way, you will not get fizzbuzz. And actually, since you are using C11, you will never get fizzbuzz on any CPU if you use these things. So, and tools like Nidhugg can help you verify that your code doesn't do something strange. Excellent. So, how are we for time? I guess we're good. Yeah, that's plenty. Okay, so I promised you a larger example. So there is this synchronization algorithm in the Linux kernel called read copy update, which lets you do atomic updates on arbitrarily large data structures by doing a pointer exchange, and then it has some mechanism to make sure that you are not freeing this old copy of the data structure until all readers have disappeared. And in order to make this really scalable, it has grown complicated over the years and is currently at over 4,500 lines of very tricky C code. And it has historically been a source of quite a few long-lived bugs that have only surfaced years after they were introduced. So in a case study, we used Nidhugg. We extracted a unit test of this thing and used Nidhugg to test this. And by reintroducing all these historical bugs, we were able to discover them. And also, in the case where none are reintroduced, we were able to verify under the conditions that, so for this particular unit test we have, and so on, that there are no more such bugs. So let me show you some of the stuff we had to do to make Nidhugg eat kernel code like that. So actually, most of the time is spent not on making the code please Nidhugg as much as it is to detach everything, to mock everything in the Linux kernel to make it a standalone unit test. So there is a lot of shims here around the primitives of the Linux kernel, like hundreds of lines of mocking that basically it takes this highly integrated part of the Linux kernel and makes it a standalone thing that you can just use to write a unit test around. So so these things are not really Nidhugg specific code, right? It's sort of it maps the thread functions of the Linux kernel onto pthreads, so on. So let me show you actually. So these things are the things we wrote, but there is of course the parts of the Linux kernel here, and these are mostly untouched. So basically the thing we touched was things like reintroducing these old bugs. So there is a lot of places like this where we have reintroduced things that were bug fixed at some point in the past. So with this, we can actually run. Let's use this terminal. Let's see if I have the thingy. There is quite some amount of. So I will accidentally teach you a bit about the command line syntax for Nidhugg. So you can pass compiler flags here, and then you have a dash dash, and then you have Nidhugg flag. So all these things I taught you before, and this is a bit scary because memcpy could very easily be used to do racy things, right? It modifies memory, but in this case, we have manually checked all places that call memcpy and see that it does nothing scary. So this is just some function that Nidhugg doesn't implement, but it could, right? This is a bit one of the things that probably as tools like Nidhugg mature, you wouldn't need to do anymore because they already understand these things and will do the right thing by default. And then we pass the name of the file, which is litmus.c, and I forgot the memory model. Let's do TSO. And yeah, since this of course takes a while, since it's so much code, and in particular there's about 40,000 behaviors I think Nidhugg explores in this one unit test, which is actually quite simplistic. Hold on, I forgot the unroll thing. So here we have also, in this code there is also this kind of retry loop, and just so that we don't have to modify the code, because that sort of makes it less clear that what we're actually verifying. If we have to change the code to check it, we're using unroll. And I need to change that because Nidhugg will eat more and more memory as the executions become longer. It doesn't really eat more memory as they become more executions, just as they become ridiculously long. So this will take about 20 minutes on a fast computer, but probably 40 on this laptop. But let's try one of these force failure flags, right? Let's try to enable this thingy and see if we can find this bug on line 1890 in RCU. Yep, found it in 2 seconds. And most of the bugs, I can show you the other ones as well, are found similarly fast. Right, this was found in 3 seconds, and so on. Right, so probably if you have a bug in your code, Nidhugg will find it pretty fast as well. But and if Nidhugg takes a while, then either it's because you have these kinds of infinite behaviors, or it's because there are no bugs and Nidhugg is actually trying to exhaust the space of all possible behaviors of your code, which for this particular example takes about 20 minutes. All right, that was the final example I wanted to show you. So there are more and more research spent on tools like Nidhugg, which are used to test this real code, right? You feed this C or C++, not some modeling language that you need to re-implement your program in. And this lets you test that the actual code that you're actually running behaves properly. A current part where a lot of work is being spent is on generalizing these techniques to the C11 memory model, which means that tools that will come out somewhat soon, we'll see when they are actually available. These are academic things, so making battle-hardened tool is not what we are sponsored for, unfortunately. But when they come out, you will be able to verify that your program not just under the memory model of some particular CPU, like we did with Nidhugg here, but that your program, assuming a correct compiler, will behave the correct way on any CPU. And of course, all the skills I taught you here will be perfectly transferable to these tools because they are the underlying principle is the same. And also, if you are programming for some other programming language, Java, Erlang, there are more. There are tools for this as well. So, to conclude, Nidhugg lets you use unit testing to test multi-threaded code, which has traditionally been a hard thing to do. It is open source. It's quite easy to compile. You just need to link it to LLVM. There's just a simple configure and make install sequence, and then you have it on your command line, just like I do. And yeah, please check it out. That's it. Do you have any questions?
Hi. What CPUs are currently supported by Nidhugg?
So, aside from sequential consistency and total store order, which is basically just Intel CPUs, Nidhugg implements, for one thing, a memory model called, well, there is another CPU that implements total store order, and that is Spark CPUs, which you might have, I guess. And Spark CPUs are also capable, at least older ones, of being configured to run a different memory model called PSO. And since it is sufficiently similar to TSO, we implement that as well. Aside from that, there is some support for the power memory model of PowerPC. But some of the features I showed you today do not work with this memory model. And it is also, the implementation is also a bit slow. So probably once tools for C11 come out, this will be preferable, assuming they get the level of polish they need.
Question.
Yeah?
Will Nidhugg be able to warn you about having non-deterministic behavior in your unit test code?
Yes. So Nidhugg looks for branches where you have places in your code where your code goes one way the first time it executes it, and then the other way the second time, and will produce a warning. There are some edge cases that will make Nidhugg just crash, but these are something we will be fixing. So yes, the short answer is yes, it will warn you. Okay? All right. Thank you.